Okay, thank you, James. Thank you for the organizers to invite me. And today I'm going to talk about scalar field dark matter, so a little bit of ultra-like actions, and a little bit more on the side of dark matter structure in collapse halos. So first of all, I just want to draw your attention to these two images here. Hopefully you can see them well. But so what I want to point you to here is that this is a typical halo that you will get in simulations just run with standard CDM. And on the, I guess on your right, you will have simulation in scalar field dark matter. And the important part of these images is that you can see that the structure of the dark matter halos is totally different. Why is this important? Well, it turns out that it's important because we know galaxies are formed in dark matter halos. And the more massive the halo, the more massive the galaxy, we believe that they're living in more massive halos. And this is important because we know that if the dark matter has different features in the halo, then that can actually have some impact on the galaxy formation. So it's not trivial to know what will be the evolution of a galaxy in a different dark matter potential. And one of the things that it's important, and it has been done, I've done some work, and a lot of people have actually found too, is that this is a very typical example of what I just said, that is in cold dark matter, you have a typical density profiles in cold dark matter halos that follow the NFW profile, so very representative of cost. So densities that grow the power of 1 over r. And if you add something else in the dark matter sector, so for instance, self-interactions, then it turns out that you can have deviations from this profile by, very large, like almost an order of magnitude. But, in this is a case for a scale for self-interacting dark matter that creates these dark matter cores that somehow, you can create like isothermal cores with these particle masses. But today I'm going to talk about scalar field dark matter, and I want to point out to one of the main features of this model. But first, I just want to say that scalar field dark matter has received different names throughout the literature, and you may actually find it as fuzzy dark matter, Beck dark matter, wave dark matter, but all of them have the same idea, and it's basically the same model. So essentially, the main idea of this model is that it has quantum-like properties on large scales, and that actually comes from assuming that the boson, or like the dark matter, is just a boson of a very tiny mass. And roughly speaking, it's usually of 10 to the minus 21, or the standard assumption is that it lies in this regime. Cosmological constraints have narrowed down a little bit, or at least have put a lower bound to this on 10 to the minus 23. But the important part of this assumption is that if you compute the de Broglie wavelength of these objects, just as Tom said in this talk, this will have kiloparsec scale de Broglie wavelengths. And that actually has an impact on galactic scales, especially the center of galaxies. And what really is going to happen is that this external, or this quantum pressure will actually add to the well, I guess it will create, avoid dark matter from collapsing in the center, so will prevent this cost. Now, because this dark matter acts more like a field, then the evolution of this dark matter, it's actually evolved with what's known as the Schrödinger-Poisson system, which is not exactly one wave function, such as Tom described a little before. So this is more like on the mean field theory. So that's why I just say Schrödinger equation. So the idea of this is that if this is the evolution equation, so systems that collapse and follow these equations and they're self-gravitating will be potentially what we know as dark matter halos. So this idea was actually explored like in the 90s and 2000s, and the simplest case was let's just look at spherical symmetric halos. And just in one dimension, let's say there's spherical symmetry, and let's evolve the Schrödinger-Poisson equation and find solutions to that. So it turns out that there's a very unique solution for that is called a soliton. And so I'll be repeating this word for the rest of the talk. I just want to clarify what it means. And a soliton essentially is just a self-gravitating solution that corresponds to the ground state of the Schrödinger-Poisson system. And this is a numerical solution normalized to dimensionless units. So what really matters here is that you have a core in the center, and they have like a very unique shape that, as I'll be talking, this turns out to be very characteristic of this model. So what we know, so this is a very simple scenario, right? So we have spherical symmetry, and this is just an isolated object. But it turns out like halos are usually formed, by mergers or other stuff, right? So it turns out that we wanted to do more, we're going to add a little bit more realism. I'll actually play it, okay. And so we started doing this in simulations that have no spherical symmetry. So here I started with, we started this with different solitons, so like the density profiles that I showed before. And then we started just like let the system evolve. And what you can see here is that there's this compact object that forms, but there's something else that forms. And there is one field that starts fluctuating, and then there's a lot of turbulence. So this is a density projection of the density field. And so what you can see here is that this object remains there for a very long term and a very long time. And then this field was not really seen in these spherical symmetric solutions. And this was work that we did in collaboration with Philip Monks, a former grad student in CFA, now in postdoc in Princeton. And so what's interesting is that if we just take one of these objects and we try to get like the density profile or some sort of a structure of what the dark matter halo will be. So it turns out like all of these object basically it follows the density profile that I showed before, and it's very well defined by this soliton solution, which is essentially a standing wave that evolves for a long time and remains there. It's very stable. And here it looks different from the other ones just because it's log density. But one of the things that we found too, and other groups have found or suggested, is that the outer part of the soliton actually seems to be consistent with an NF-double-like profile. Now the problem here is that this transition, as you can see, it's not very clearly defined. And the reason of that is because there is a turbulent field that sort of interacts with the soliton. So what we wanted to do was to actually count a little bit more on this transition. So one of the things that we did was just like run 100 simulations with different initial conditions, such as like the one I showed before, these idealized simulations. But we wanted to have some control of that. So it turns out like we actually found that there is actually some scatter in the transition. So here are just like different density fits, density profiles, just NFWs fitted to our simulations. And so these are normalized densities to their central density. And what's interesting is that if you normalize all these density profiles for these different 100 simulations, so all of them follow this soliton profile. And it turns out like the soliton density profile can be well approximated by this analytical formula, which was found in Skiv et al., which I probably forgot with the reference here, but I'll show it later. But the important part that I want to mention here is that if you only take a look at the inner parts of these halos, so you can very well fit them with this density profile, and it really depends on basically one parameter. And this actually comes from some scaling symmetries from the Schrodinger-Poisson equation. But as you can see, basically the central density depends on the mass of the boson. So here's normalized. M22 means it's normalized to 10 to the minus 22 EVs. And it really depends on let's say one parameter that typically is chosen as the core radius. So if you just look at the dependency, you can see that halos that are denser will have the smallest scores. So this is very interesting. We actually wanted to do more of an analytical description of this. And we know that these halos are very dense solitons, etc., but we wanted to tie that to some quantity that's more global, like the halo mass or some viral mass, right? So for that, we needed cosmological simulations. And so this is something that we've been doing, and this is one of the simulations that we've been running in collaboration with the same group, the same people. And so here's one of our simulations in a 2 meter per second box, which is, I know it's limited in size, but the point that I want to mention here is that if you compare this simulation with this mass to CDM, you can really see that there's a lot of structure that doesn't form here, and there's another interesting thing here that even though there is like a suppression of superstructure, the structures that do form do not necessarily follow the same evolution as a CDM, and that's very interesting, and we're exploring that right now. Now, this is at redshift 3, but fortunately there's been another group that's also working on that, and they did this with a different code, so called Gamer, and which is an adaptive mesh refinement code. And it turns out like they follow, for instance, one of these halos through time, and then they look at the density profile with high resolution all the way to redshift 0. And so this is the density profile at redshift 0, and they just track the evolution at different times. And yeah, okay. And it turns out like the density profiles of the very center of the halos, it really follows this solitonic profile that I just showed before throughout time. So one of the important things here, that we have to note is that, as I said, we wanted to have, now that we have this kind of simulations, now we can start thinking about the inner and outer halo transition. It turns out like they actually found a formula that fitted this, they found a relation between these two quantities. So like they parameterized the inner soliton by, say, the core radius, and then they tie it to the halo mass. So, and they just found this fin parameter, fin, where's the coefficient? And so now we know that this relation actually ties the inner and outer part of the halo. And one of the things that's important to note is that the problem that we are having now in simulations is that resolving these solitons takes quite a lot of computing time. So it makes it really hard to start exploring this in a broad range of masses, especially for the higher masses, because the solitons get smaller. So that requires even more resolution. So, so the important thing here is that with this relation and the fact that, as we saw, there is some scatter in the transition, then what we did was to actually come up with an analytical formula to describe the full dark matter halo in scalar field dark matter. And the way to do that was basically we assume mass conservation, say within the Vero radius, and then we just say the inner part is going to be the soliton, and the outer part is going to follow in the NFW, and the transition is going to happen at some predefined soliton radius, which is just the parameter that's going to tell you where the transition happens. And so this is a very robust result, because what we are actually proposing is that this model actually works for any halo mass. So this allows to look for, to search for the parameter space in a way that we can't really do in simulations. And so that's what we did. So here are just like two density profiles for two halo masses, typical halo masses. So like for dwarf halos, around 10 to the 10. Here's 10 to 11-ish. So roughly Vmaxes of 40 kilometers per second, and here's 100. And this is the scatter that comes from, as I said, this interaction between the turbulent field and the soliton. And the solid line is the scalar field dark matter, and the dashed line is typical CDM. And you can see, for instance, for dwarfs, that the soliton, it's always for the mass that shows in here, so like the dilution mass of 2.5, for instance, that's still within the limits, and observable limits, let's say. So it turns out like for dwarfs, the scalar field dark matter halos are actually less dense. But as you go to higher and higher halo masses, then the solitons start becoming denser. So then at some point, especially for Milky Way masses, you can actually see, I mean, you can sort of figure out, but like this is going to become even denser at some smaller spot rate. So now we are at the stage where we can compare the observations. And just to remind you, there's the TBT fear problem that people have argued in cosmological cold dark matter simulations with dark matter only. And it seems like there's these massive halos that are above the classical Milky Way dwarfs, and that apparently they don't have any counterparts, observable counterparts. And in Papstorius and Shankar, they actually found that there was some observations at larger rate that actually make the problem worse. And so what about scalar field and typical field? So it turns out that if you plot all the density profiles in here for like two different halo mass, two different particle masses, but just one halo mass, so say typical dwarf, so 10 to the 10 solar masses, then you can see that the outer part or just the scatter that comes from this turbulent field, it actually makes a better description for these outer points, especially because, as I said, this is the region of large radii where effectively feedback is not very efficient. So it turns out, like we found, is that scalar field dark matter actually does better to describe it too big to fail, but we also have to make sure that it happens this propagates in different problems, right? Like that it can solve different problems, trying to say. So here's the Costco problem that you already know. So basically, you have galaxies that sometimes have like Schauer profiles, and what we did to compare with just sort of get an intuition of what scalar field dark matter does with Costco problem. So we selected LSV galaxies sort of from this Vmax range from Spark Rita, which are galaxies that are 10 to the 8 to 20 to the 9 solar masses. And we found that, in fact, if you choose the same two scalar field masses that actually work for the 2 big T problem, they don't really work for to solve for the Costco problem. And in fact, they do. They are actually denser for higher boson masses than CDM. So what it's important to note is that this happens basically within 1 kiloparsec. And that's the regime, again, where feedback can actually affect. So at least just from this simple comparison, what we found is that scalar field dark matters are actually more discrepant than CDM within 1 kiloparsec, even though they make better predictions for 2 big fail. So just to conclude, here is basically the game that I've been playing for a couple of years. So what we're actually doing, or what I'm actually doing with all the dark matter exploration, is that we're trying to do is, we have all these tests, these observational tests, and future tests that are going to come, and we want to understand, what dark matter actually fits all these tests. So I'm just going to leave you with these questions, and just a quick spoiler. So we are basically now at the point of starting some projects with scalar field dark matter with hydrodynamics. So I'll leave it. Thanks.
Okay, let me ask the next speaker to come up and plug in, and we'll take a couple questions.
Hi, so I was just trying to make an analogy with what mathematical physics means by the word solid for what
Right.
problems with mass matter like solutions and non-differential equations, nonlinear differential equations that solutions that are in a phase superposition. I just couldn't understand in your talk how you were associating solid terms with any wave.
Right. Yeah. So So this is a little bit more elaborated than that. So it's the idea of this model is that these particles have huge de Broglie wavelength, and then when you have these halos that have 10 to the 10 solar masses or so, you have a huge number of these bosons. So at some early time in the universe, they will be having overlapping de Broglie wavelengths, and then at some point they will start becoming like coherent. So what we show with what we actually found with the simulations is that this coherence gets a little bit lost after a certain radius, which sort of happens at the de Broglie wavelength. So as long as you can have the gravitation, whatever. So as long as you can have these objects, I guess like being stabilized by gravity, then it seems like a fluctuating field somewhat like erases this coherence. Yeah.
Okay, one more quick question, Tom.
Have you thought about cluster mass how things all on there?
Right. Yeah. So if you follow, great question. So if you follow the scaling that would show for this equilibrium halos, then in principle you should expect to see very high densities and small cores. But at the level of clusters, and this is something that we've been discussing too, is that usually they're made of very big galaxies, and it's not just like one single galaxy that collapses. So it's not clear that this quantum wave interference in a very like a many body system of galaxies actually follows the same scalings. So.
Thanks, Victor.